All right, so we're going to be doing a financial example using exponential growth with derivatives and integrals, and we're going to be relying on the continuously compounded. So an account with $5,000 compounded continuously has a rate of 5%. So we know that this is our principal, our initial amount, and this is our rate, and we got to convert it into a decimal. And so it allows us to plug in everything like that. And so now we can use this to calculate how much money we'll have in our account with a 5% interest, initial amount of $5,000 after a certain number of years. So after 10 years, all we have to do is say A of 10 is equal to 5,000 e to the 0.05 times 10 and plug it in our calculator. Oops. And it gives us $8,243.61. So 8,200. I already forgot it. Let's just leave it up. 43.61. There we go. And make sure you have the dollar sign. And that's to the penny. So if you have a continuously compounded account with 5% interest with $5,000, that's how much your account would be worth in exactly 10 years. Now, we want to use the derivative. And so if you remember our derivative formula, right? However you look at it, if we take the derivative of p e to the rt, we're going to just rewrite it and then take the derivative of the exponent. So if we have a of t is equal to p e to the rt, then our derivative would be p e to the rt times the derivative of the exponent, which is p e to the rt times r, and that's where we're getting it. So it's just RA. So all you have to do is put the rate in front, and you have the derivative. So what's our rate? 0.05. What was our A? 5,000 e to the 0.05 t. And it also makes sense if you just go, I'm just going to take the derivative. I don't want to think about this. You're good. It's 5,000 e to the 0.05 t times the derivative, which would be 0.05. So now we can plug that in our calculator to multiply it. And 5,000 times the rate is now 250. And we need units. So we always want to go back and go, well, what does A equal? A is in dollar and time is in years. We deal with years when we're doing the count. And where am I getting this from? Well, if it's A prime of t, that means we're dealing with dA dt. So whatever we get here is going to end up being in dollars per year. So it's going to tell us the amount of growth per year. Okay. All right, so now what does that mean? So we're going to use it on part B to see why R is called the proportionality constant. Okay, so first, what is the rate of change of the account at 10 years? So this is what we're going to be using because part B is 10. So if we plug in 10 into our derivative, that's going to give us our rate of change. So 250 e to the 0.05 times 10, and then we'll go back and answer that question. It's good to know everything about these problems. So 250 second e to the 0.05 times 10. And this gives us 412.118. 412.18. So what we're looking at is at 10 years, we should expect a growth of $412 per year. So what does that mean? So this is telling us what our expected growth is for that next year. So this is our expected for the next year. Now this is compounded continuously, so this is an underestimate, but there you have it. All right, so why is R called the proportionality constant? So if you take this right here, the 412, and divide it by that, what do you think you're going to get? So to make this perfect, we're going to go up and grab that one and then divide it. So proportionality means how are they related as a ratio? So we are going to take this one and divide it by that one. And look what you get. 5%. Because it makes sense. What are we expecting here? So at this amount, we're expecting a 5% growth rate. That's all that is. Look, this is our function here. So if you were to plug in 10, it would give you this. Well, how much do we want? 5% of it. And there you have it. So that's all this is saying. This is the amount that we're getting at that point. And we just want 5% more. That's our expected growth. This is supposed to be 10 years. So our rate of change is 412.118 per year. So that's what we're expected. So at 10 years, we want $412. So we're expecting a growth of $412.18, right? From 10 years to 11 years. Now, you don't want to put it as an actual rate of change constant because these aren't constant. This is just an approximate. So this is our expecting. So you can also say an expected growth. Okay, so now let's take a look at another one. What is the rate of change of the account at 30 years? So we're going to be now looking at our rate of change at 30, and you'll see why in a minute. So 250e to the 0.05 times 30. And let's plug that in our calculator. Okay, bring up the calculator. All right. So you can see now it's 11,020 and 43 cents. 1120. See, what's happening is as your account grows, it has more money. So that 5% gain that you got here is still going to be a 5% gain here, but you have more money in your account. The key with investments is that you want to have money in your account, and that takes time in order for that to happen. So I'm going to put expected this time. Expected growth of $1120.43 from 30 to 31 years. All right, so that's an okay amount. I mean, you're going to have a lot of money in that account, but what we really want to do is invest constantly, and that's where our integral comes in. So if you invest $5,000 each year for 30 years, that would be a total investment of $150,000 over, I got a lot of typos in this, but I don't have time to go back and redo it. A total investment of $150,000 over 30 years. Then we could also now use an integral. So an integral is going to add up all of those investments. So it's going to take the first one, which is $5,000 for 30 years. That's that one. And then it's going to take the next one, which is $5,000 for 29 years. And the next one, which is $5,000 for 28 years, and so on all the way to the end. So this integral will give us an annual investment of $5,000 per year with our interest rate, and we're going to use 5%. So now if we plug that in, we get 0 to 30 of 5,000 e to the 0.05 t dt. So now if we use our integral, we know that this becomes 5,000 over 0.05. We can use u substitution to do that. 30 to 0. Now we just double check it. So the derivative of this would just be this exact same thing times the rate, and the rate would cancel, taking us back there. So it's perfect. So now we're just going to plug in 30 and 0. We end up with 5,000 over 0.05 bracket e to the 0.05 times 30 minus e to the 0.05 times 0. And that last one is just 1. So we can just plug in 1 when we do our calculator. All right, so let's move it over a bit. So that's what we're doing here. The integrals add up all of these values from 0 to 30 years. And so this is going to give us, if you just put in $5,000 a year, how much will be in your account with an interest rate of 5%. So 348. So you only put in 150,000 and now it's 348. And if this is a tax deferred account, that was all interest. So you just made twice as much. 348,168.907. But you didn't put it in. You're putting in, think about it this way, you're only putting in 5,000 per year, right? And so you can increase that amount and you can increase the interest rate. So a standard mutual fund gets 8%. So you can see where everything goes. That's just the rate, right? Rate and then amount. So this is really 5,000, 0.05 e to the 0.05 number of years minus 1. So we can now make a formula. It's P over R, e to the R t minus 1. So you can now plug anything you want in there, like this. So if we now do 6,000, that's 500 a month And if you do a 403b or 401k, that's not going to cost you $6,000 because it's going to be taken out pre-tax that you would have paid tax on anyways. It's a win-win. It's $500 a month. 8% is what you can get as an average return with mutual funds. And there you go, $751,000. So you can increase these a little bit more, play around with it, and then you can see how much you need to put into your account for 30 years. But that is the key. You want 30 years for this to happen. We have doubling rates going on here. So if you did ln of 2 divided by 0.08, it doubles every 8.6 years. And so the better the interest rate, the more it doubles, the more money you have. Like looking at the 5, the 5 doubles every 13. So you can see just by getting 3% more, you're going to make a lot more money in the long run. But time is the key because you want it to double and double and double and double and double. Like 2,000 becomes 4, which becomes 8, which becomes 16, which becomes 32, which becomes 64, which is 128 and 256 and 512. It gets big fast, and then you're over $1 million. Right? So there's your uses. Derivatives tell you the rate of change for the year. If you divide it by the amount for that year, you're going to come out with the exact rate because that is the growth. It's a 5%. And if you take the integral of that exponential function, it gives you the amount for constant investments.